So this talk is about the ultra-reliable low latency connectivity. So this is highly related to the vehicular networks. So this is Vehicular Technology Society chapter. So then this ultra-reliable low latency connectivity is highly related to the vehicle to vehicle or vehicle to infrastructure networks. So you all are familiar with the 5G use cases. So in 5G, we have a enhanced mobile broadband and massive machine type of communications and ultra reliable low latency communications. But if you take the 6G use cases, so all these three use cases are going to be strengthened. So here we are going to have strengthened enhanced mobile broadband, strengthened massive machine type of communications, strengthened ultra reliable low latency communication. So in the 6G, there are some other new use cases as well in addition to these three pillars. So if you take the top one, enhanced mobile broadband, so it's going to strengthen for different new applications, high data rate applications. If you take the left-hand side, a strengthened massive type of communications or massive IoT. So here this is for smart building, smart city, smart home. If you take the right-hand side bottom, so we are going to have ultra reliable low latency communications. So here this application, this use case is related to the V2X, vehicle to vehicle or vehicle to infrastructure. So here, if you take the vehicle to vehicle or vehicle to infrastructure, the main thing is the latency, because if you take driverless autonomous car, so then the latency should be the critical issue, otherwise there will be accident. So at the same time, here we need ultra reliability. So if you don't have the reliability, so then the transmission may not be effective. So therefore here in V2X, we are going to have ultra reliable low latency communication is needed, vehicular networks. So in 6G, we are going to have one new use case, massive ultra reliable low latency communication. So that is the combination of massive IoT network with ultra reliable low latency communication. So that means it is a combination of the bottom two pillars. So that is massive machine type of communication and ultra reliable. So here we have a new use case, massive ultra reliable low latency communication. For example, if you have huge number of autonomous vehicles, so that is massive. So we need ultra reliable. The latency also should be very, very low, less than 1 millisecond. So now the question is, when we have in 6G, so in this massive ultra reliable low latency communication, so how we are going to achieve? So massive connectivity, ultra reliability, low latency, all these three requirements should be satisfied. So if you take the from 5G to 6G, so everything we are going to have extreme. So if you take the left-hand side, we have extreme data rate, extreme coverage. So everything related to the enhanced mobile broadband. So the high data rate. But here, this talk is about the right-hand side. So massive ultra reliable low latency communications means massive connectivity, extreme low latency, extreme high reliability. So that means in the right-hand side, three requirements to be met. So that is, if you take extreme low latency, so less than 1 millisecond. So extreme high reliability is going to be 99.9999%. Extreme massive connectivity means, so here 1 square kilometer, we are going to have 10 million devices are going to be connected. So how we are going to achieve this? So now we are going to take one by one. How we are going, we could achieve extreme low latency. How we could achieve extreme high reliability. How we could achieve extreme massive connectivity. First, we take extreme low latency. If you take the extreme low latency, so that means less than 1 millisecond. How we are going to achieve this less than 1 millisecond? If you take the conventional communication schemes, they use grant based. If you take all the existing standards, mainly grant based. Grant based means user equipment is going to process multiple handshaking process before actual data transmission. For example, once from the user equipment, if the packet arrives, so going to send the preamble, then the response from the base station, then connection request, connection setup, then only the permission granted, so then data transmission. So if you take the top diagram, so here we are going to have so many handshaking process, so we are going to have high latency. So if you take grant free, so that means we don't have this prior handshaking process or schedule request. So user equipment is going to transmit the data to the base station as and when the packet arrives in the user equipment. So now the problem is, so here in the grant free, we can reduce the latency, but here without any scheduling, if you transmit the data, we are going to have collision. So there's a problem here also. In the grant free also we have problem, because as and when the packet arrives in the user equipment, if it transmits immediately without any handshaking process, then collision will occur. So that means the data transmission won't be successful. So that's what here we have, whether grant based or grant free, we still have problem for these three cases. For example, so here we have the three requirements: massive connectivity, so low latency, high reliability. When you take the massive access, here we have limited preambles. So that means user equipment will have to select a preamble from the limited pool. So when you take the latency, if you have grant free, as I said earlier, we are going to have collision. So because of the collision, there should be a retransmission. So by that way, the latency still will increase. So then when you take the reliability, so there will be frequent collision. So how we can improve the reliability? So we can see, so how we are going to achieve. So if you take the grant free, we can reduce the latency, fine, but we are going to have frequent collision. So that means how we are going to improve the reliability and how we are going to improve the massive connectivity, we'll see. So here, if you take the conventional schemes, so orthogonal schemes, when the orthogonal in time domain, or orthogonal in the frequency domain, or orthogonal in the code domain. So that means the resources are allocated for a particular user. So if the resources are allocated for a particular user, so we need for massive connectivity, we need huge resources we need, but the resources are expensive. We may not be able to have infinite resources. So one potential solution is to remove the orthogonality. If you remove the orthogonality, so the same frequency at the same time is going to be utilized by many users. So that is here, if you remove the orthogonality, so time frequency resources are going to be utilized many users at the same time. So with different signature pattern. For every user, there's a specific signature pattern. So at the receiver, it uses the successive interference cancellation to separate the users based on the signature pattern for a specific user. So when we have grant-free, we can reduce the latency. When we remove the orthogonality, we can increase the connectivity. So therefore, to meet the two requirements, so massive connectivity and low latency, so grant-free NOMA is a potential solution. Now, how about the reliability? So here, non-orthogonal multiplexers provide the massive connectivity. Grant-free provides low latency. Now, how we are going to improve the reliability? To have the high reliability, so in the 3GPP standard, two types of repetition schemes are recommended. One is K repetition scheme, other one proactive scheme. So what is the K repetition scheme? So here the user equipment is configured such that it is going to transmit same packet for certain number of repetitions. So same packet, for example, you are going to repeat again and again, for example, 10 times. So base station, what it is going to do, it is going to decode each repetition independently. So, and the transmission is successful, at least one repetition succeed. So by this way, we can improve the reliability. Instead of transmitting the one packet, the same packet is going to be repeated certain number of times, 10 times. So definitely it will succeed one of the 10 times, 10 repetition times. But the problem here is if we have more repetition, so latency will increase. So therefore, so we have to reduce the number of repetition as much as possible. So here the base station send the acknowledgement at the end of the last repetition. For example, if you have 10 repetition, each repetition decoded independently. For example, fifth repetition is successful. Even though the fifth repetition is successful, the acknowledgement from the base station will be sent to the user equipment at the end of the last repetition for 10th repetition. So this will increase the latency. So that's what, instead of sending the acknowledgement at the end of the last repetition, in the proactive scheme, so here, so user equipment terminate the repetition once it succeeded. So it does not need to wait till the last repetition. For example, if the second repetition is successful, so it is going to send the acknowledgement to the base station, sorry, to the user equipment, and is going to terminate. So by that way, we can reduce the latency while increase the reliability. So because of that, this proactive scheme is better in terms of improving reducing the latency while improving the reliability. So now, here we looked three schemes. One is grant-free, other one is non-orthogonal, other one is repetition scheme. So these three schemes, grant-free, NOMA with repetition, is a potential solution to achieve three requirements: massive, ultra-reliable, low latency. To achieve these three requirements, so here we are going to have grant-free, non-orthogonal, and repetition scheme. Okay, so now we know that so grant-free NOMA with the repetition scheme is a potential candidate for the new use case in 6G, massive ultra-reliable low latency communication. So here in LTE, we know that resource block. So one resource block is going to be 180 kilohertz and 1 millisecond. So here the contention transmission unit is, so with physical resource block, here we are going to have multiple access signature. So that means if you take the LTE resource block, we have in frequency domain and the time domain, 180 kilohertz in frequency, time 1 millisecond. But here, contention transmission unit, here we have one more dimension, that is the signature sequence. So the signature sequence, actually, it consists of two things. One is pilot sequence for user equipment activity detection, and other one is a set of code book for data transmission. So that is called multiple access signature. So here the third dimension is multiple access signature. So frequency domain, time domain, and we have the third domain is the signature. So here we are going to have contention transmission unit. Contention transmission unit, for certain number of units we have. So actually, contention transmission unit means actually physical resource block with multiple access signature. So now, so we know that grant free with repetition scheme. So it's the solution for massive ultra-reliable low latency communication. So what is happening in the uplink? So if you take the uplink, so in the user equipments, so the packets are going to arrive. So base station, the inform the resources and parameter configuration. So first step, the packet arrival in the user equipment, base station. So it decides the parameter configuration. So then user equipment is going to choose the resources for transmission. So that is first two steps. What is happening in the base station, what is happening in the user equipment. The remaining, so here we have the latency constraint. Because here the requirement is, we have the latency maybe 2 millisecond latency or 4 millisecond latency. Or here we need less than 1 millisecond latency. So we have latency constraint. So if it does not meet the latency constraint, it is assumed that packet lost. The next one is collision, because here grant free. So since it is grant free, so the more than one user select the same CTU and transmit to the base station, so collision will occur. Then here we have non-orthogonal multiple access scheme. So here we are going to have successive interference cancellation at the end for decoding. So here latency check, collision detection, data decoding, all three should succeed. So step 3, step 4, step 5, everything should succeed to send the acknowledgement to the user equipment. So what is, say here CTU collision means? This is the way CTU collision occur. For example, here we have CTU pool, 6 CTUs we have. So user equipments are going to select randomly, one is going to pick up one CTU and transmit to the base station. Say here if you see this diagram, for example, user equipment 2 and 3, they select the CTU 2 for the transmission. So collision will occur. 4 and 7, they select CTU 1, collision will occur. If you take user equipment 1, so it takes only the CTU 6 is only taken by user equipment 1. CTU 5, user equipment 5. So no collision. So if you take CTU 3, it is idle. No one selected the CTU 3. So when you have the contention transmission units, CTUs, so we can have 3 groups. One is idle, other one singleton, only one user select the CTU. Other one collision, more than one user select that particular CTU. So in that case, the collision will occur. Okay, so now, so we have seen the potential solution for massive ultra-reliable low latency communication is using grant-free, using non-orthogonal multiplexers, and repetition scheme. For these three requirements, still we have numerous challenges. Even though grant-free NOMA with repetition is a potential solution, why here we are going to have challenges? Because the active users and the channel conditions are unknown to the base station. Then here we have the constraint, latency constraint, reliability constraint should be satisfied. Then here collision will occur. More than one user select the same CTU, the collision will occur. So here we have the optimization framework. So it's complex because we have communication environment complex. Here the problem is model deficit. Here we don't have a tractable mathematical formula. So here we cannot use the conventional convex optimization. So we can use only non-convex optimization. So now what would be the solution? So if you have model deficit, if you have a model, then you can use the convex optimization methods. Here we don't have model because of complex environment. If you don't have the model, what is the solution? Solution is the machine learning. So whenever you have model deficit or algorithm deficit, so machine learning is the suitable solution, because so they are going to learn, they are going to use the environment, so they are using the learning experience, so they make the decision. So the decision they will make based on the learning experience. If you take the conventional solution, we have model, then we have the theoretical approach, so independent optimization, and we have the short-term key performance index. But if you take the machine learning, so it's a computational approach, so we can have cooperative optimization. Here we consider long-term key performance index, not short-term. So that's what this, so machine learning based approach works better whenever we have model deficit or algorithm deficit. So this problem is a model deficit problem. So therefore we use the machine learning. Here we considered one specific machine learning approach, that is the deep reinforcement learning approach. So when you take the deep reinforcement learning approach, here we have three things. So that is observation, action, reward. So here we have agent. We can have multiple number of agents. So the purpose of the agent, so agent is a software. So the agent, so what is the function of agent? Agent is going to observe the environment. So what happens during the previous transmission time interval? So it is going to observe what happened during the previous transmission time interval. What happened? After that observation, it is going to dynamically select the parameters, that is the action, such that the long-term reward could be maximized. So here, what are the observations? So 5 observations during the previous transmission time interval. What is the number of collision CTU? So what is the number of idle CTU? What is the number of singleton CTU? So that means during the previous transmission time interval, okay, certain number of CTUs were idle, certain number of CTUs collided, certain number of CTUs succeeded. Okay, so that is 3 observations. The next one, even if it is succeeded, so that means successfully detected, when they do the decoding, So they may fail. So there are two scenarios. So that means successfully detected and successfully decoded. Other scenario, successfully detected but unsuccessfully decoded. Decoding is not successful. So these are the 5 observations the agent is going to observe during the previous transmission time interval. Based on these previous observations, it is going to make an action. So the action means, so here if you take the repetition scheme, repetition value should be dynamically changed, because if the channel condition is very bad, the repetition number should be high. Then only we can achieve the reliability. When the channel condition is very good, so we don't need the high repetition value. So therefore, repetition value should be changed dynamically. So that's the function, that is the action of the agent. Then the number of CTU. Number of CTU means, so here the CTUs, resource blocks, are expensive. So therefore, we cannot waste the resource block. So if now the traffic is, at the moment, traffic is very high, then we need to allocate more CTU. If the traffic is light, so we don't need CTU, so we don't need to waste the resources. So we can select only few CTUs, the remaining will be utilized for some other purpose. So therefore, the agent will have to choose the number of CTUs and the repetition value dynamically. So these are the 2 agents we are going to have in the base station. So when they select this action, they have to, there are many possible actions. There are many possible repetition value. There are many possible number of CTUs, but they have to select the correct repetition value, correct CTU number, such that the reward could be maximized. What is the reward? So here the reward is the number of successfully served user equipment under latency constraint. So here each agent is going to maximize the long-term reward. So here the agent, the deep Q network agent, so it is going to calculate the Q value, and so for which set of action the maximum Q value comes. So it calculates Q value and select the set of actions, those give maximum Q. Or it can take random action, say exploration and exploitation. So 90% of the time, exploitation. So that means exploit the Q value. 10% of the time, it takes random decision. So random action, exploration. So now, what is the traffic scenario we are going to have? So traffic here, so the packet arrival, say we have normal traffic and bursty traffic. Normal traffic means, for example, the smart meter, smart electricity meter, smart water meter, everything. So it's a normal traffic. So it's not a problem. But here, for example, if you take pay as you drive, it's a bursty traffic. What is meant by bursty traffic is, during a particular time interval, huge number of user equipments try to access. For example, if you take pay as you drive. Pay as you drive insurance means, say now at the moment, so we pay for the car insurance is fixed. So monthly this amount or annually this amount. But pay as you drive means you are going to pay for insurance only when you drive the car. Say 2 days, if you park your car at home, you don't need to pay the insurance. So whenever you take the car to the road, so the sensor will try to establish the connection through the base station to the insurance service provider. insurance service provider, so allow, okay, your car is now insured, you can drive. So once he come and when he park the car, so the sensor will inform to the insurance service provider, now I park my car, so you don't need to pay the insurance. Now, for example, if you have a big football match, so 10,000 cars will leave after the football match. All these 10,000 cars will try to establish the connection with the base station. So that means we have limited CTU. So everyone will take the CTU from the pool. Then what will happen? Collision will occur. Say, for example, if you have 20,000 devices try to establish a connection, success rate around only 20%. So that means only 4,000 cars will be succeeded to establish the connection and drive. So remaining 16,000 will not be able to drive the car. So that is the bursty traffic scenario. So if you take the 3GPP standard, the recommended, so time limited beta distribution is the suitable mathematical model to model the bursty traffic scenario. Here we can see high traffic, low traffic, the bursty traffic scenario with different parameters, alpha, beta. We can model it. So now what we did, okay, so here we are going to see the performance of these two agents. So here the two agents, one agent is going to dynamically change at the beginning of each transmission time interval. It is going to select the suitable repetition value by observing the previous transmission time intervals. So here repetition value 1, 2, 4, 6, 8. So out of these 5 repetition value, it is going to pick up 1. It can be 4, it can be 8, it can be 2, it can be 8, 1. So that depends on the observation. Previous observation, it knows that, okay, so how many collided, how many preamble succeeded, CTU succeeded, how many detected and decoded. So from that observation, he knows the channel condition roughly and decide the repetition value according to agent. Similarly, the CTU number. Okay, traffic is heavy or light. If the traffic is light, so it can allocate CTU only 12 during the remaining not necessary for some other purpose. So now traffic is very heavy, so select 48. So that means out of this 12, 24, 38, 36, 40, it is going to select one of the CTU number at the beginning of the transmission time interval. So here we consider the scenario, one base station, the user equipments are within 10 kilometer radius. So here we have the number of user equipments, 20,000. 20,000 distributed within the 10 kilometer radius. So the agents, here we have 2 agents. So they have 3 hidden layers. Each layer have 128 rectifier linear units. And when we do the 1000 training episode, so here we have the constraint, latency constraint 2 milliseconds, and we consider the path loss exponent and all the parameters. So here bursty traffic distribution is alpha, beta, 2, 4. Here we found that, so the proactive under bursty traffic scenario, the proactive scheme performs better than the repetition scheme 1.5 times, because here we have to meet the latency constraint. If you take the repetition scheme, it decodes till the last repetition and send the acknowledgement. In the proactive scheme, it terminates well ahead. So because of that, it can meet the constraint, latency constraint, so the success rate high. But K repetition scheme, it won't meet the constraint, so it's failed. So therefore, here proactive scheme is better. So here we can see how they say here, if you take fix the value. So that means repetition value is fixed 8, or CTU number fixed 48 CTU. But if you see the agents, 2 agents, so you can see the red line, they reduce the repetition value based on the environment. They reduce the number of CTUs based on the environment. So compared to the fixed value, so here they reduce the latency means they can improve they can reduce the latency further by having low repetition value, unnecessary to have high repetition value. So similarly, say we can save the CTU numbers as well. Now, here we have single configuration grant. But in 3GPP release 16 standard, they proposed multiple configuration grant to reduce the latency further. What is multiple configuration grant? If you take the multiple configuration grant, so now you know the 5G new radio, new mURLLC. So not like LTE, in 5G, we have a different number of subcarrier spacing, and we have the number of slots vary, say according to the frequency, subcarrier spacing difference. Say for example, in 60 kilohertz subcarrier spacing, we have the subframe of 1 millisecond is divided into 8 slots. So that means each slot 0.125 millisecond. So here we have 8 slots within one subframe. So within the slots we have 7 OFDM symbols. So in the multiple configuration grant, so here what happens? So as and when packet arrive, so if you have only single configuration grant like earlier, so if the packet arrive in the middle of one subframe, the packet will have to wait till the beginning of second subframe. So that means, so packet arrive now, so in the middle of 1 millisecond. If it arrives in the middle of 1 millisecond, so for example 0.5 millisecond, it will have to wait till the beginning of next subframe. So that means 0.5 millisecond delay. So in multiple configuration grant, it is not necessary to wait. So that means it can start the transmission not at the beginning of the subframe, at the beginning of a slot. So here each slot 0.125 millisecond. So that means the waiting time is going to be less than 0.125 millisecond. Say here if you have single grant, so maximum waiting time may be 1 millisecond, because so one subframe started, just after the started packet arrived, so it will have to wait 1 millisecond. But in multiple configuration grant, packet arrived, so it will have to wait maximum only 0.125 millisecond. So by having that one, so we can reduce the waiting time from 1 millisecond to 0.125 millisecond. So here, so that is the multiple configuration grant. Say here, for example, here we have 4 configuration grant. First one, blue, yellow, green, red. So here, the first configuration grant, so the transmission starts at the 0th time slot. Second grant start at the first slot. Next, second slot, third slot. So therefore, when the packet arrives, user equipment select the suitable configuration grant. So for example, if the packet arrives at the end of second slot, so it will select configuration grant 4 because it can transmit the data at the beginning of the third slot. So therefore, by having this, we can reduce the waiting time from 1 millisecond to 0.125 millisecond. So because of that, we can reduce the latency further and further to meet the requirement of sub 1 millisecond latency. So here, the same thing like single configuration grant, here one more agent. So here why we have one more agent? Because which one is the best starting slot? So for that particular user requirement. So that agent tells to the user requirement, okay, select this slot, this grant. So here we have one more agent. So all three agents cooperatively maximize the reward, the successfully served user requirement. So here same like earlier, here you have the CTU number. It is going to be one of the value, age 16, 24, 32, 40, 48, 56. One of this value at the beginning of the transmission time interval, one agent will select the number of CTU. Other agent will select the starting slot. Starting slot 0 better or 1 better, 2 better, 3 or 4. Other agent will select the repetition value, whether repetition value 1, 2, 4, 6, 8, which one is better. So these three agents select from one of these discrete sets. So the same scenario, base station at the center, user equipment located within 10 kilometer radius. So here we have three agents. Each agent have three hidden layers, each layer with 128 rectifier linear units. So here we considered low traffic and high traffic. So in the low traffic, so here single configuration grant or multiple configuration grant performance, say if you take red and green, almost same because the low traffic. But in the low traffic, but bursty the 30-40. So here multi-configuration grant perform better. Now we are going to see high traffic and bursty. So when you have high traffic, so huge number of devices and bursty. So here we see single configuration grant completely failed. Green and black completely failed. But multiple configuration grant works well. So that's what the 3GPP standard in release 16, they recommended multiple configuration grant. Because of why multiple configuration grant? By selecting the suitable grant, we can reduce the latency further and we can meet the latency constraint. So now you can see the latency in single configuration grant under bursty traffic and multiple configuration grant under bursty traffic. You can see multiple configuration grant latency, it meets a requirement. Less than 1 millisecond is the requirement. So multiple configuration grant meets the constraint of less than 1 millisecond. So therefore, multiple configuration grant with machine learning is the potential solution for the new use case of 6G massive ultra reliable low latency communication. Now you can see. So we have configuration grant multiple 2, 3, 4, 5. So when we have more and more configuration grant, we can reduce the latency further and further. Say here, the red one, when you have 5 configuration grant, latency is less than 0.8 millisecond. Here, the number of successfully served users is high because we can meet the latency constraint. So therefore, if the latency constraint is not met, we assume that it's failed. So therefore, multiple configuration grant with machine learning is the potential solution. The solution is for the new use case of massive ultra reliable low latency communication. Here, considering the different background of audience. I haven't included any mathematical derivations. I just provided the concept of massive ultra-reliable low latency communication and what would be the solution to meet the requirements. So the details are available this year, April JSAC paper, the first one, and the last year JSAC paper in the second one. So multiple configuration grant is in the most recent paper, April 2022. So you'll find the all mathematical details. Okay, so now you have any questions? So my allocated time 45 minutes. So I finished on time. So now if you have any question.
Yes, sir. Thank you, sir. Thank you very much. Sir, audible? Hello, sir.
Yeah.
Yeah, audible. My voice is audible.
Sorry. Yes. So no, not clear. Can you tell me again?
My voice is audible, sir.
Yeah. I can hear. Yeah, I can hear.
Yeah. Can you hear me? Okay, yes, sir. Sir, I have one doubt.
Yeah.
Actually, we in 5G use cases, we talk about shortest distance in kilometers, maximum 1 or 2 kilometers only. But for 6G use cases, you have taken some 10 kilometer radius as reference distance. I don't understand.
Yeah. So here for just for simulation purpose, we considered 10 kilometer because then only we can have 20,000 user equipment distributed. But in the standard, it's not going to be 10 kilometer.
Okay. Just for simulation purpose.
Sorry?
Just for simulation purpose,
Yeah, that's only for simulation purpose. Yeah.
Actually, what will be the distance coverage for 60 use cases, sir? What will be the distance, expected distance coverage for 60 use cases, 60 communication use cases?
Yeah, in 6G, they are going to have small cells. So they are going to have ultra dense cellular network. So that means, so to increase the coverage, in addition to the macro cellular network, so they are going to have small cell networks.
It's a small cell network means maximum 200 meters something.
Yeah, few hundred. Yeah.
Meters only. That's why I'm asking.
Yeah.
Then only we can expect this kind of low latency. I hope I understand like that only.
Yeah. So now the research topic is in edge intelligence to reduce the latency further.
Yes, sir. Edge intelligence. Okay, sir. Okay, sir. Then what about the power expected transmission power, sir, for 60 use cases? Transmission power requirement.
The transmission power.
Yes, sir. Yes, sir.
The transmission power, the compared to the 5G, say here in the 6G, so almost same the transmission power. So here, only thing is the connectivity and the other two requirements.
Yes. Okay. Okay, we are discussing, we are concentrating the connectivity. How fast we can able to get the connectivity quickly, the response.
Sorry?
How fast the devices are able to get the connectivity. That is the issue we are concentrating in 6G. Yes, sir?
Yeah.
Connectivity issues.
Yeah, so the connectivity is the issue here. Okay. Because of the billion number of devices.
Yes.
So to increase the connectivity, so now the research work mainly on dynamic optimization. So that is the artificial intelligence enabled optimization, dynamic optimization schemes.
Okay. So we are concentrating how we can provide connectivity in a faster way to the connected devices. That is the objective of 6G use case.
Yeah.
Yeah, I got it, sir. Because we are familiar, very much familiar with the 5G use cases, and we are into the 5G use cases in India. So that's why the 6G use cases are very new for us.
Yeah, because that is only in the initial the research status. So so now they consider to reduce the latency further, and the edge intelligence, so cellular connected UAV and few other schemes.
Then any other domain they are concentrating under 6G, sir?
Sorry?
Except this low, there is latency part. What
Yeah.
are the other domains they are concentrating in under 6G? Except this combination.
Yeah, so the other one is they consider for the massive IoT. So the massive IoT, cellular-based massive IoT networks. So there also, so even though the data packet volume is very small, but the number is huge. So that one also, massive IoT also is another research direction in addition to this critical IoT.
Okay. Okay. How many years it will take, sir?
Sorry?
How many years it will take to use this case, 6D use cases, tentatively?
So now in 2022, maybe in another 5 years.
Another 5 years it will take to reach or to use this 6D use cases.
Yeah.
Thank you, sir.
Sir, good evening, sir.
Yeah.
Sir, I have a small query, sir, regarding the handoff techniques in 6G. So what will be the handoff technology we'll be using for 6G, and what is the time for looking over it?
Handover?
And a handover, yes, sir, handover timing. When you're going for 3G and 4G, you go for massive assisted handoff and all those things. For 6G, is there is any specific terminology for looking at defining over it?
To be honest, the new handover technology for in 6G, I am not familiar.
Okay, sir. Okay, then regarding with respect to coverage area, sir, when comparing the existing, what will be, it has a more number of increased size, sir, coverage area.
Yeah, so to increase the coverage, so network densification is the another research direction.
Okay, sir. Okay. Thank you, sir.
Good evening, sir.
Yeah.
Sir, I just have a small doubt. Now, since we are talking about cellular IoT devices, so they are usually simple and they are power-aware devices. So if they want to get connected to the 6G air interface, will the complexity of the construction increase? Because they have to support the 6G air interface and also the encryption protocols and integrated protection algorithms. So hardware-wise, even the complexity of cellular IoT devices, will it be prone to increase?
Yeah, definitely. Yeah, it will increase. Yeah, because when we have this number of devices, so the security is then another challenge. So definitely the complexity, hardware complexity will increase. Yeah.
Okay. And what about the sub-carrier spacing? Because for currently 5G, we are going to have up to 960 kilohertz sub-carrier spacing. So in order to further reduce the latency, will we go beyond this 960 kilohertz flexible numerology?
I don't think it will go further and further, but within the existing subcarrier spacing, the alternative solutions would be the suitable one.
Okay. Okay, sir. Thank you, sir.
Sir, any questions from other members? Sir, is there any research work going on regarding this health issues, health hazards of cellular towers?
Yeah. There are several newspaper articles about the health issues for when the carrier frequency moved to 3 gigahertz. But I don't think they verified experimentally, or they have any clear evidence. I don't think so. Any evidence?
No evidence, but many discussions are going on about the health hazards
Yeah,
of
because
piracy and registry.
because there are so many articles, so many video clips in the media, but the experimentally not verified yet.
Why they are doing like that, sir? Why such kind of unwanted news are coming? Is there a really existing, or some they want to exploit or spoil the technology?
They say that normally when the carrier frequency move up, it is harmful.
Oh. Which comes under ionizing radiation part.
Yeah. So even current 4G, 5G, the radiation effect on the health issue is still unknown. Maybe the 4G, 5G carrier frequency also maybe not good for health. It's still not verified.
What is your feedback, sir? What's your suggestion? Whether we can proceed with this 5G, 6G use cases and applications, or shall we restrict ourselves? What is your suggestion, sir?
I don't know about this health issue.
As a researcher, you have to provide some solutions because we are all working in this domain only, wireless domain, and then we are doing research in the small cell and associated health hazards, but we are not finding any good solution to arrive finally. Yes, sir. Yes, sir. So, any other questions from the participants? Kindly unmute yourself. You can unmute yourself, or you can put it in the chat box. I will ask on behalf of you people. Any interesting question you have, you can ask Professor. So very happy to have today as a speaker today. So we are very much honored to have you speaker today, sir. Thank you very much. On behalf of IEEE Madras section, PTS chapter, the chairman, and I'm very much thankful to you, sir.
Okay, you are welcome.
1 minute. Speak on, sir. Speak on, sir.
Yes, ma'am. Yes, ma'am.
Start the moment.
Recording in progress.
Participants, if you are, if possible, switch on your camera for a photo with Professor. Take 1, 2, 3.
Ma'am,
Yes, sir. Share.
ma'am, I couldn't able to share the screen.
Online. You are the okay. I will make it. Yes, sir. How are you?
Yes, ma'am. I can. Sir, kindly accept this on behalf of our IEEE Madras section VTS Society section.
Okay, thank you.
Kindly accept the CE moment, sir. When you visit Chennai, definitely we can have a meeting there. Hello, sir?
Okay, okay.
Yes, sir. We wanted to have a meeting with you. Okay, sir. Thank you, sir. Thank you very much. Now I invite Dr. Vijayendra Babu, sir, to propose vote of thanks formally. Please, sir.
Good evening to all of you. On behalf of Vehicular Technology Society VTS Madras section chapter of IEEE Madras section, I place my sincere gratitude and thanks to the guest of today's event, Professor Dr. Arumugam Nallanathan, Professor of Wireless Communication, Head of Communication System Research CSR Group, School of Electronics Engineering and Computer Science, Faculty of Science and Engineering, Queen Mary University of London. So the session was really an interesting, and it was an eye-opening session for every one of us. As in India, we are now just experiencing the 5G implementation only in select cities. Now the research topic is on 6G, which has given us given a clean idea for all the faculty members and researchers who have been working on it. I myself personally as a many key takeaways for today's session, as we have talked about more about the multiple access technology. We just taken about the NOMA, which has been bringing since we were just taught from the scratch, just to put it like a point wise, just all those things like grant free, grant configuration grant, then most intuitively multiplication configuration, and what is the need for it, and what is a significant application for it. And especially when you touched about the massive ultra reliable low latency, you just highlighted that the latency reducing from 1 millisecond to 0.25 milliseconds. So all the parameters was implemented and tested. It was a very good, useful for every one of us, sir. We hope this meeting would have been made to having more collaborations with you in future on various platforms. Thanks for your presence, sir, and thanks for the entire members who are present here to make this second event of Vehicular Technology Society a grand success. And I sincerely thank our chairman, Dr. S. Brinda, and the whole team who has been preparing to make it happen, and for attending at the evening session as per Indian time. Thank you, everyone. Thanks for the cooperation.